Welcome everybody on Zoom. Welcome everybody in the lecture hall. Today we are going to continue and maybe finish, if we have time, on wine column stores, knowing that I will take the time to explain, I will take the time to answer your questions, because as I say, it's a bit tricky material. In fact, I think that in what you will see in this hour, a lot of new pieces of the puzzle will come and make sense probably for you. You will see. Before we start, I will ask you two questions, two understanding questions on the Clicker app. One of them is something you already know, and the other one something that is the cliffhanger question of yesterday. So this is the first question. So, you know, we see key values all over the place in this course, but in particular, in HBase, in the physical level, we also saw key values again. So what are the key values in HBase? Is a key value the smallest units of physical storage indexed by column and version and sharded by column families and time intervals? Is it the smallest unit of physical storage indexed by row and column, sharded by regions, column families? Is it the smallest unit of physical storage indexed by row, column, version, sharded by regions and column families? Or is it the smallest unit of physical storage indexed by row ID and sharded by regions? Let's see if you agree. We do have a majority. The question is the majority correct? It seems that many people are now joining the majority. Let me not make you wait any longer. The majority is correct, indeed. So the key, there are two things here, the key and the sharding. The key has the row, the column, and the version. We saw that it's a version system. So this is what uniquely identifies a value, right? So the row would be the horizontal coordinate. The column, meaning the column family plus qualifier, is the vertical coordinate. And the sharding is done both by region and column families, meaning there's horizontal sharding and vertical sharding. And everything that is in the intersection of a region and a column family, this is what we call the store. And this is how it's grouped on the physical storage. Something else that we saw is that in terms of responsibilities, the region servers are assigned entire regions, meaning that even though there is sharding that separates the column families, the responsibilities are always horizontal, in the sense that if you're responsible for a region, then you get the responsibility for all the column families within that region, right? Even though they are stored separately. Okay, very good. Let's move on to a second one, which is kind of my cliffhanger of yesterday. Why is that? That we have a system HDFS that is known not to have the greatest latency. It's not really instant when you query something. And yet, HBase is much faster running on top of HDFS. Why is that? First, you might not agree. Maybe you think HBase is not faster and it has a high latency like HDFS. Or it's because HBase has key values in the mem store as well as in caches. Is it because it short circuits data nodes? Is it because it uses smaller HDFS block sizes? Should be a big B here, 64 kilobytes. Again, this question is not about something you already know. It's about what we are going to continue to do, right? So this is why it's more of a guessing game than checking knowledge. Because this is something I haven't told you yet. have a majority. And it turns out there are two correct answers. The first answer is that indeed the key values, as we will see, are not only persisted on HDFS, not only. There are also the fresher key values that are actually held in memory. And how that all works, when do you take it from memory, put it on disk, or cache it in memory and so on, we will see today, right? But the trick is, it's not always reading from HDFS every time. There are a lot of key values in memory. The second answer about short-circuiting data nodes is something that is a general principle in big data. It's not only HBase. Actually, we see that MapReduce does the same, and Apache Spark and so on. The idea is that, as I told you, the region server process and the data node process, they are running on the same machines, right? You have 1,000 machines, let's say. Each one of these 1,000 machines runs a region server process and a data node process. When the data node stores the blocks that it's responsible of, so the data node stores the blocks, where do they go, these blocks physically? Where are they? Yes, go ahead. You can throw the catch box. Let's see if the volume, maybe we need to increase. Oh, is the receptor actually plugged? Oh, that's this is very funny. I think we didn't plug the receptor, the receiver of the box. Oh, sorry. Yes, here it is. Sorry. So I need to increase the volume here. Let's try again. Can we hear you now?
Can you hear me? I think so. So the data is, the data node process is going to take care of storing the data. So it's going to be stored on the same node if it's the first replica, and otherwise it's the same process that HDFS uses.
Yes, exactly. So indeed, you store one block replica on the same as the client and then on some others. But physically, in terms of hardware, where is that? On the physical level.
It's the same machine, right? It's the same storage that both processes have access to.
Okay, how can you find it? Let me just directly tell you. What I mean is the local disk, right? So every node, every one of the nodes on which you run the data nodes has a disk attached, a hard drive, SSD or HDD. So the replica of the block is a file sitting on the hard drive physically that is attached to the node. And indeed, as you said, this is absolutely correct, that you have one replica that is going to sit on the same machine as it was created, as the file was created, and then two others at some other places. What is very important to understand is that physically, it's sitting on a physical hard drive as a file on the machine where the data node is running, the data node process. What does that mean? It means that the region server process running on the same machine can read the replica of the block right from the local drive, because it's a process running on a machine reading from a local drive. This is what we call short-circuiting. Normally, why is it short-circuiting? Normally, when you use HDFS, you connect to the name node and then you communicate over the network with the data nodes, right? So normally the region server, if it was using HDFS like anybody else, should communicate using the HDFS protocols over the network in order to get the blocks. However, since the region server process so happens to be running on a machine that where the data node is also running, it can cheat. It can cheat by directly reading the file from the hard drive where it sits. Who understands that? Yeah, very good. This is what we call short-circuiting, and that actually makes it faster because you don't get the network latency and so on. And this is something we'll see again in MapReduce and so on. All right, so let me now go back to the slides. Yeah, I'll get to you. Let me put the slides. All right, so there was a question there, yeah?
So as part of the HDFS exercise, we already tried to read data of file in HDFS from the same machine as the same machine as the the machine that put the file in HDFS. So that should be a read, a local from read from local storage too. But we saw in the exercise that it still takes a few seconds just for HDFS to talk to the name server and everything. So when you're talking about this, you're talking about the same thing, or just is another level of cheating, like directly knowing that the file is there and accessing it local without going through HDFS. I don't know if it's clear, the question.
So I will confirm offline because I don't have the exercise on the top of my mind, but I would say from what I hear, if you mentioned several seconds, it's a whole new level of cheating. In the sense that you really completely bypass the name node, you completely bypass, everything. And the reason why you can do that is that HBase, first, it's developed by the same people who develop HDFS. So they basically can have a lower level of interaction. They know how HDFS works. And second, because what happens is that the region server process is going to cache some of the information. For example, when you communicate with the name node, it tells you where the blocks are, where the locations are, where the block IDs are for a file, and so on. And this is something that the region server is going to keep in a cache. So it doesn't need to ask the name node every time. It already knows. And when it knows that a specific block ID is stored on the same machine, which it also knows from the cache, then it reads directly from the disk. And then reading from the disk, of course, is much faster than a second, right? So it's still, there is still a latency. I can't remember. I'm not a hardware person, right? But I think a latency on a hard drive is in milliseconds or dozens of milliseconds, right?
Yeah, that was exactly my question. So it bypasses the normal HDFS interface.
Yep, exactly. Yeah. And regarding the exercise, this is where I have a doubt, so I would need to see it. But yes, it completely bypasses the name node and the processes. Yeah. Okay, thank you. All right, and continue to ask many questions. That's exactly the goal, right? I want to make sure that you understand what's going on, because of course we're looking specifically at HBase, right? But a lot of the principles we are learning, they are more generic than just HBase, right? They are really very important for big data. So as a reminder, we have this model with the row IDs, with the column families and column names and so on. And we saw that we shared it. It's like a pie that you share with your friends, cutting horizontally and vertically. And then you have these intersections of regions and column families that we call stores. And within a store, this is a single store, we have the individual cells that are actually stored sequentially as key values. And we saw that the keys here are the row ID, the column family and column qualifiers, so the column name, plus a version. And we saw there's also a version. And then the values are here. So we saw once we understand that, we can go down the whole hierarchy of what we store. There is the entire table. We partition it horizontally, we get regions, right? These are intervals of row IDs. Next, if we shard it vertically, we get the stores, right? Every column family within a region gives you a store. Within the store, we have on the physical storage, so here I mean what is going to be persisted to HDFS, we have H files, one or more H files, and we'll see today how these H files are created and how it is that there can be more than one. Within an H file, we saw that there are H blocks, and within the H blocks, there are the key values, and every key value gives you one value corresponding to a row, a column family and qualifier and a version. Okay, for whom is that clear? Okay. Now I had a few pending questions, and maybe now is the right moment to tell you about these H blocks and the index. You know that in an H file, it's just an ordered sequence of key values. But in order to make things faster, I told you that the H file doesn't only have an ordered sequence of key values, can be a lot of that. It also has a separate structure that is an index. And the way the index works is that the key values are organized in blocks of 64 kilobytes plus, right? And there is in a separate section, the first key of each one of the blocks, right? So you have a list of the first keys of every block. And then what happens is that when you read an H file, you load in memory this index, then you scan through the keys and you know exactly what H block to look for or to read from disk if you are looking for a specific key. Now the question was, is there more structure to it than just a flat list of the first keys of every block right in there? And the answer is actually yes. I looked around a little bit, and there are actually later versions of HBase or of H files that actually structured the index not in a flat manner with just a list of the first key per block, but on additional levels of depth of the index, meaning that you have the first key per blocks that are themselves stored on an intermediate layer, themselves again in blocks, and then an upper root nodes that contains the first, let's call them meta block, right? There's the blocks, then there's the meta blocks, and then there's the root. I'm not sure if I'm making any sense actually when telling you that. Does it make sense to anybody? Okay, let me try to re-explain better. Imagine, let me do it with numbers. Imagine you have 1 million key values in an H file, 1 million of them. Imagine that, I'm oversimplifying, right? Imagine that every block has 100 key values. Of course, it's not always the same, but just for my example, 100 key values. So it means that I will have how many blocks in total? 1 million key values, 100 per blocks. How many H blocks are there? 10,000, right? This is what I'm hearing, exactly 10,000. 1 million divided by 100, 10,000. So then you're going to think, okay, if I just write the flat list of the 10,000 first keys, so for every one of these 10,000 blocks, they have a first key in them. So the index would contain the list of all the first keys in every block. So it's a list of 10,000 keys, right? That's still a lot, right? So if I would directly do that, in memory, I would still have to scan through 10,000 keys in order to locate my H block. So it's not optimal. So what happens is that what we do is that these 10,000 blocks are themselves organized in bigger blocks again, meaning that I'm going to again cut that in 100, meaning that I have now, let's say 100 indices of each 100 blocks. 100 times 100 is 10,000, right? So now I have 100 indices that each handle 10,000 key values. And what I do is that then I add yet another level on top that is a list of 100 keys, right? 100 keys. And what you do when you look up is that you look up at the top level in the 100 keys. This is something fast. You locate the index block that you need to look at. Then you go one level down. And then you again look up in the list of the 100 keys the exact H block, right? So you just do it on multiple levels. Did it make sense? Who understands what I said? Oh, that's good. Yes, do you have a question? So you're asking in the sense of information retrieval, right? The skip pointers or? Oh, that might be. I will answer offline because I'm not entirely sure. Let's take a note and I'll come back to you. Yeah, I think indeed in my. Yeah, I think I also saw that when I was investigating. So I'll come back on that. Yeah. Okay. So this is it for this index. But actually, we'll come back to that in a few weeks because when we study document stores and MongoDB, we will look at the way that indices are built and indices at multiple levels. So this is something we will come back to. Okay. So now the problem we have is that when we write that down to the disk, it's an H file we write to HDFS, we can only write, there's no random access. We just have to write it from the beginning to the end. And on top of that, we must write all of that in sorted order of the keys. So how do you insert a new key then? Imagine that you want to insert a key right there between key 8 and key 9. You cannot just append, right? You would need to overwrite the whole thing and then offset everything. So that's something that you cannot do in HDFS. We don't know how to do that. So we need to find a way to circumvent that. So how do you insert new values? And the idea is that when we read the data, the key values, they are stored in H files on HDFS, right? So that would be on HDFS, but also in memory. What happens is that in the memory of the region server process, we store the fresh key values, the ones that have just been created very recently by the user. We keep them in memory and do not yet store them in an H file. You know that for the memory, it's easy. Adding something in memory, you're not constrained by appending things. So what's going to happen is that you're going to use a data structure in memory, probably a tree or something, that maintains the order of the key values, but you know that we can do that efficiently in logarithmic time. We can insert any key values in that structure. So I didn't draw the tree here, but basically we maintain in what is called the mem store all the recently added key values in a structure that maintains the order. Okay? And what happens is that when you write a new cell, you add it to the memory, right? So here's a new cell, here's another new cell, and then at some point, you add so many new cells, so the users use HBase so much and added so many values that the memory is full. So what do you do when the memory is full? You do what's called flushing. You flush everything to an H file. So what is happening here? Well, first, you get a free lunch, because since I told you that these key values, they are already in a data structure that maintains their order, how much time is it going to take me in complexity, in algorithmic complexity, to list them in sorted order? What's the complexity of that? Yes? Linear, exactly. It's linear. Why? Because I have a data structure that already maintains the order. Otherwise, it would be, of course, n log n, right? But my log n, I already had the n log n, I already had by inserting them every time in log n. Yes? That could be a heap, that could be anything that maintains the order. Could also be a tree, you know, it doesn't have to be a heap, but it can be a heap, right? Okay, so this is why I'm not saying more precisely than that. It's any one of the structure that you studied in algorithms and data structure that maintains an order. So it means that in linear time, I can traverse the entire list of the key values that are in memory, and I can actually output them one by one to an H file. Now, this is great, because if I traverse in order and write them one by one, I'm just appending things to my H file. So this is exactly what I'm going to do. I'm going to traverse my data structure in memory in linear time, and I'm going to flush. If it's a heap, for example, I'm just taking on top of the heap every time the next key value, and I'm flushing them to an H file. Then at the end, so it's block by block, right? I keep track of the first key in every block. And at the end, when I have flushed them all, then I also flush the index, which is the list of the first keys of every block, right? Okay. There is one more thing that we need to be careful about. We saw that things can go wrong. And if I have my fresh key values in memory, what if the machine crashes? Then I lose them. Right, so that's a problem. So how do I make sure that even if there is a problem and the machine crashes, I won't lose them? This is done with what is called a write-ahead log. It means that before I get to insert my key values in memory, I keep a journal somewhere of everything that I add, but not sorted by key, sorted by the order of insertion, meaning that, again, appending things. I keep appending to a log in order of insertion all of the key values. This is called a write-ahead log. It's called an HLog structure that also goes to HDFS. And since we are appending things, this is all good, right? So now if the electricity, if there's an electricity shortage or whatever, or the machine crashes, we're safe because we have everything in the HLog. So we have the H files for the older values, and the newer ones are going to be in the HLog. They are not going to be sorted by key in the HLog, but they are still here. We can recover. Yes? The catch block is over there, I think.
Yeah, so I was going to say, when it comes to the HLog and the flushing process, I suppose we just write on the node that the data node is running in as well and such, but I was wondering in the context of HDFS, is it that when the data node does it, every few hours that it sends the actual files that it has, that the name node will see that there are new files and it will start to replicate them? Or how does the actual process of going through HDFS works in the case of HLogs and the actual flushing process?
So this is all going through HDFS for the HLog and for the write-ahead log. This is all going through HDFS, meaning that you go through the regular process of talking to the name node, creating the file. You have the replication pipeline to go to several of the nodes. It's important, right? Because if you don't go through the regular, so you mean not short-circuiting, imagine that we short-circuit and the machine crashes, then we lost everything again. So we need to go through the official channel of HDFS, have the replicas, and so on, right? Was it your question?
Yes, yes.
Okay, awesome. Do you have another question? I think I saw raise hand. Okay. So, oh no, that was on Zoom.
So the question is, the heap for ordering of the key value pairs, doesn't the heap take O of log n for each pop? By pop, he means retrieving the max value.
Oh, that's actually a good point. So it might be, this is also something that I look at. It might be indeed that the heap would be too slow for getting the linear time. We look at it offline because I don't trust, you know, when I'm presenting live, I don't trust my brain to the original thinking. We'll check that. We need to be careful indeed about that. Is that we need a data structure in memory that inserts in log n every time you insert something, but you need to be able to take it out of the structure in linear time. And now that I think you're absolutely right, it might be that with a heap, it would be n log n to extract, indeed. That's a very good point. Thank you for mentioning that. Yeah. Okay. All right. So we have the write-ahead log, and everything must first be logged before it's inserted in memory. Okay, now we're safe. The machine can crash, and we don't care. So we flush whenever we reach the threshold for an individual store, an individual region server. We can also keep track of the total number of key values in memory in the entire cluster. We can also put a threshold there. If the total number of key values becomes too big in the cluster, we flush everything. And we can also trigger a flush when we reach a full write-ahead log. The write-ahead log has become too big. Okay? So this is how we write. So now, how do we read? Well, we read from everywhere. Because if you look for a specific row ID or a specific column family, it could be anywhere. It could be in the H file on the left. It could be in the H file on the right. It could be in the memory and so on. So we just look everywhere. And everywhere we try to gather, maybe it's a scan or range query. So we found all of the green or dark marked key values in there. And you see some of them are fresh in memory. Some of them were maybe added a month ago and they are sitting in the H files there. And we just gather them all. And then this is shipped to the user, right? This is going to be the results of the query. For whom is this clear? All right, so this is when we read. Then something else is going to happen. What if I keep using HBase so much and so much and so much and so much that I flushed once, twice, 3 times, 10 times, 100 times? Then at some point, I'm going to have so many H files on the disk that it's becoming unmanageable. Because every time I read, I need to look at all of these H files. How do we deal with that? Well, there is something else on top of the flush that's called a compaction. A compaction means that we take all of the H files there and we merge them into a single H file. And we again have the sorted key values, but all merge. What is the complexity of doing that? There's somebody who never. Okay, let's go to you, then I'll alternate. Yes, go ahead.
I was going to say it's linear because the values are already sorted, so we just have to do the merge part of the.
Yes, exactly. It's linear, exactly. In fact, it's the second half of the merge sort. Remember the merge sort? It's the second half of that. You've already pre-sorted the batches, and then you merge. And indeed, it's just a concurrent traversal. You have a pointer in every file, and you just concurrently follow the pointers and navigate in parallel over the files. So indeed, linear time. Very good. So this is compaction. Okay. Who is following? Okay, so we saw 2 things. We flush from memory in linear time when the memory is full, and we compact when we have too many H files. Now, this would be the naive way to go. In fact, in the earlier version, the way to go, you just compact when the number of H files is too big. The problem is that it's not efficient, because if you look at even bigger periods and you just do it that way, you will quickly notice that it doesn't really scale if you just flush and compact naively in that way. So this is why we have something that is absolutely fundamental in big data, and this is probably the most important thing to remember from HBase. It's something called log-structured merge trees. And log-structured merge trees are a protocol or a way to structure things that makes it very efficient to do big data analytics when you want to be throughput oriented. And this is in the case of HDFS, HBase, big data, it's throughput oriented. You just want data to flow around. You do not want latency to block you, right? So the whole log structured merge tree, which I'm going to explain in a moment, is motivated by the idea to be throughput bound. The data must flow around, right? I'm contrasting the log structured merge trees with index structures that you find in relational databases, for example, called the B plus trees or the B trees. Who knows about B plus trees and B trees? Quite a few of you, right? We'll see them again when we study indices in the document store. So even if you don't, we look at them. But basically, the idea of a B plus tree is that it's seek time bound. The whole motivation behind a B plus tree is that every time you access the disk, you need to pay a latency. You need to wait, if it's a mechanical drive, for the head to arrive. So the B plus trees are structured in blocks in such a way that you fetch entire blocks at a time from the disk. So it's going to be dominated by seek time. It's for point queries, you know, looking for specific values as efficiently as possible. Okay, so this is just here. I'm putting the two on the slides, B plus trees and log structured merge trees. This is what LSM trees means, log structured merge trees. I'm putting them in contrast with each other, right? This is seek time bound, it's latency bound. This is throughput or transfer time bound. Okay, so the way it works on an abstract level is that the data is organized in a hierarchy of structures as opposed to a single structure. So first we have what is in memory, then we have what has been flushed to disk, right? So far, we actually saw that first level, that's the mem store, right? Everything that is in the mem store. Then it's flushed to disk, so that would be levels, if we call that C0, that would be level C1, right? This is what has been flushed to an H file. And when you compact to an even larger H file, that's the next level of C2, right? So as you can imagine, the H files that have been compacted are going to be larger than the H files that have just been recently flushed, right? The more you compact, the larger it gets. So you have C0 in memory, C1, it's just been flushed, and C2, it's been flushed and compacted. And it goes on, C3, C4, C5, and so on. So you see that these are the more recent values, and the more the values age or date back in time, the more you are going to push it down to compacted and compacted and compacted again data structures. Okay, but I have even better than that because that is too abstract. I actually have an animation for you that I prepared. And then hopefully it will all click and you will see what's going on in here. Here's how log structured merge trees work. Here's a mem store. I haven't flushed anything yet. There is nothing in H files yet. It's a brand new system, a brand new created table that is in there. So now I have 1, 2, 3, 4, 5, 6, 7 key values that are in the mem store. Okay, the mem store is full. What happens? Flush. Yes, I flush everything to an H file. There you go. Okay, now the memory is full again. What do? I flush again. Okay, and now what I'm going to do is that I have 2 H files, so I'm going to compact them, merge them, it's called compaction, to a larger H file. This is twice as big. right? If this was size 1, this is going to be size 2, right? Now the memory is full again. What do? I flush again. I create an H file. The memory is full again. I flush again. What happens now?
Sized H files.
So what is the name for that? Compaction, exactly. So I compact them. And now we again have 2. And we do again a compaction. So now this is size 4. Do we have a question on Zoom?
If the writes in the mem store are from different stores, do you flush it into different H files?
Oh, yes, absolutely. You really need to keep in mind that we sharded things by column family. So the stores are separate. We only ever flush what is in the same store. Everything that is in there is exactly the same column family. This is all the same column family. If there is data in a different column family, in a different store, it's going to be a completely different and separate structure for doing that. Did it answer your question? Okay, awesome. Okay, the memory is full again. What do? We flush. The memory is full again. What do? We flush. There are 2 H files. What do? We compact. Okay. The memory is full again, we flush. The memory is full again, we flush. There are 2 H files, we compact, and so on and so on and so on. Who understands what's going on? Okay. Who realizes that we are just counting in base 2? Let me go back for the others that you will see it. You need to look it, invert it. When you count normally, the larger exponents are on the left and the lower on the right, right? Here is the opposite. Okay, let's count in base 2. These are exactly the same slides, but now I'm looking at interpreting that in base 2. This is 1, 2, 3, 4, 5, 6, 7, and so on. Who sees it? We are just counting in base 2. That's it. That's how it works. This is the log structured merge tree. And that means that we keep the number of H files under control because we have this elegant logarithmic oriented way of scaling up the size of the H files. And by the way, those who are in information retrieval already know that because we've already seen that also in information retrieval. Right? This whole idea when we have the indices that we merge when this is an online index construction. Who remembers that? Okay, so for you, this actually wasn't new, and this is called log structured merge trees. And again, this is super important because the idea of log structured merge trees goes beyond just HBase and white column stores. This is a very generic way to process. It's like some magic system that transforms dynamic updates like transaction, not transaction oriented, but write oriented. You write a lot of small things and you manage to convert it magically to a system like HDFS where you have high latency. And so you need to minimize the number of writes. In order to do that, you use that kind of structure to write it to disk. In fact, the high level concept that we see here, it's batch processing. It's the idea that we are writing to HDFS in batches. This is in contrast to writing every time there is a new key value. That would be very inefficient. We write in batches, meaning one very big H file at a time. Do we have a question?
As the size of the H file as it goes deeper in the LSM trees, do we also have index that are deeper within the H file?
Yes, the index becomes deeper, but there is something else. Can anybody guess what's going to happen if the number of H files, even with this, grows so big? What is going to happen? Can you guess that? Yes? It is the idea of splitting something. The only thing that is not quite right is that it's about the blocks. The idea of splitting is exactly the right direction. You want to split, but what do we split? what do we want to split here? Yes, maybe the catch box so that people can hear you. But this is 80% of the answer already that you gave, yes?
Maybe we split the region in two.
Exactly, we split the region in two. That's exactly what happens. And remember, this is something that I showed you on a slide yesterday. The region has just become too big if the H files are growing too large. So the H master is going to say, okay, now we add an additional separation, an additional bounds as a row ID, and we split the region into two separate regions. And then what's going to happen is that there is a process that will rewrite and split the H files into the H files for the first half and the H files for the second half, right? For whom does that make sense? Okay, so I hope that with this, the pieces of the puzzle start assembling, right? One by one, that it's all making sense together, what's going on here. Okay, so what's more, we cache things is that in order to accelerate and to not have to read everything from disk every time, we actually can cache the least recently used, the most recently used key values in there. It's very important to understand that this is not like the mem store. The mem store is the freshly created one. The cache contains those that have already been persisted, but recently used. We have a question here. Maybe could you please throw the catch box? Thank you. Oh, oops. Go ahead.
Is this splitting of the region done by the H master or the node themselves?
It's decided by the H master. So the H master gives the instruction, okay, now we split. And then it's the responsibility of the region server to then go ahead and implement the splitting.
Does the H master realize that the region has gone too big?
I have a doubt now. It could be, so if it's the decision of the H master, it could be that it's with reports, the same way that you have reports in HDFS, that it goes all the way up to the H master and that the H master makes the decision to split. But now that you're asking the question, I have a doubt if the region servers cannot spontaneously decide to split. It might actually be, it might actually also be that it's been changed. So thank you for asking that question. That's an excellent point. If you think, independently of HBase, the whole thing, the idea of splitting, if the H files goes too big, can be taken as a standalone decision by the region servers, right? I just have a doubt of what HBase does now, if it goes through the H master that decides or if the region server does it. So let's also add it to what I will get back to you about. But thank you for asking the question. That's a very good point. It's critical thinking, that's exactly what we want at ETH. Okay, and a question here, then we are going to stop for today. For the caching, let me. All right. For the caching, does the HBase also have query-specific caching strategies such that overwriting most recently used or least recently used? I think that there is indeed, it's not really the material that I cover, but there are caching strategies. There are even several kinds of caches and several levels of caches in the system. I just explained it here on the very high level, right? Okay. So it's great, you asked a lot of questions. I'm not going to finish, that's okay. I'm going to finish next week with the material, but I'm really glad at all the questions that you asked, right? So this is great. We went into details. I also have a bit of homework to do to get back to you on some of the questions. But congratulations, you've made it. I mean, hopefully now you know how log structured merge trees work. All right, so thank you very much. And I will see you next week on Tuesday on the continuation of that, and then we look into data models. Thank you very much. Goodbye.